All right, I want to welcome you to the second of our lectures today. How many of you were here for the first lecture? A lot of you. Okay. Well, I apologize to you. You're going to hear a lot of the same spiel about some of the other events going on, but bear with us for a second because some of the people weren't here for the first lecture. Basically, my name is Tim Swindle. I'm the director of the Lunar and Planetary Lab. So I want to welcome you to, and we can phrase this a variety of ways. This is officially Moon Month in Tucson by declaration of the mayor. This is this whole set of events celebrating the 50th anniversary of the Apollo 11 landing is known as Moonfest, and we're sort of in coordination with other groups all over town. And in particular, there are 3 other venues on campus. There are some maps showing where things are, and moon balloons, which I'll get to in a minute, sort of guiding the way. And this is also Lunar Planetary Lab here. We always do a Summer Science Saturday, so this is our Summer Science Saturday. So welcome. Let me tell you a little bit about some of the other things going on here in the Kuiper Space Science Building. We have a number of things out on display. We have some informational posters. We have memorabilia. We have a moon rock or 2. We have a variety of groups that have come and brought things of interest. We also have people in the, and that's all sort of outside here. We have 1 floor up, the Regional Planetary Imaging Facility, which started with, finding a place to collect all the best images of the moon, what images there were, and has grown from there. There are people up there that can talk to you about what we've got there. Unfortunately, we have tours of our new nanoscale material characterization facility in the basement, but those tours have all, they're all booked fully, but if you are on one of those tours, I don't mind if you step out, at the time of your tour. Next door at Highlands Science Center, otherwise known as the Planetarium, there are a variety of events for families, including planetarium shows. They have one called Capcom Go, which is just running for this month. Across the University Mall at Special Collections in the University of Arizona Library, they have an exhibit. Its grand opening is today, although we will be running through the end of the year. But Special Collections, they have both rare books and they have archives of papers, people's papers. So among the rare books are a couple of first editions by a couple of guys named Galileo and Copernicus. There's a lot of memorabilia from a guy named Ewan Whitaker, who was at LPL for quite a while. In particular, he was the one who picked out the landing site for Apollo 12. They have a number of things from his collection. He was also a collector of all things moon related. And a number of things from his collection, though not my favorite, which is the a book about the mission autographed by the astronaut saying, "Thank you for finding our landing site for us," which we have outside here. Also have a globe from a project called the Rectified Lunar Atlas, where to take out the distortion that you get from taking a 2-dimensional image of a 3-dimensional object. Telescope images were projected onto a globe, and people would walk around taking pictures of it to see what it would look like from overhead at different places, and that's on public display for the first time ever, I think. It may have at some point in the 60s, but I'm not sure. Then there are tours of the Mirror Lab, which last I heard were not booked up yet. And as I say, you can find them by the string of moon balloons, and I'm proud to say that we do have moon balloons, so such a thing did not exist 6 months ago. Also in town, there are activities going on at the Children's Museum right now. The loft is showing Movie for All Mankind at 2, and Professor Bill One from LPL will be there. The Desert Museum is having a program this evening at 8 p.m. And Matt Starman, one of our graduate students who works on lunar things, will be speaking there. And there's more stuff going on in the coming weeks and months. Today is the big day, of course, but all of this stuff is at moonfest.arizona.edu. This is the second of 3 talks. So there will be another one after this one, and a number of you were at Bob Strom's talk. This one will be by Professor Jeffrey Andrews Hanna. Jeff got his PhD from Washington University in St. Louis. He spent some time on the faculty at the Colorado School of Mines, and then as a research scientist at Southwest Research Institute before joining our faculty in 2017. He works on a variety of topics, including a bunch of lunar ones. And so without further ado, help me welcome Jeff Andrews Hanna.
Thank you very much. So it's a pleasure and an honor to be here on the 50th anniversary of Apollo. I'm the token, I guess, post-Apollo lunar scientist. I represent the generation of lunar scientists that never actually got to see a person walk on the surface of the moon. But I'm going to talk to you today about the scientific legacy of Apollo, things that we learned from Apollo. Now, I wanted to start off just introducing Apollo, but having not been there when it happened, this seemed like a bit of a daunting task for me. So rather than me tell you anything about Apollo, I thought I'd just show you a quick video. You heard from Bob Strom about a lot of, let's see, try so that can work. All right, there we go. About Apollo 11. I just want to show you a quick video because on this day today, everybody should watch the launch and should watch the landing at least once. You've already done it, my apologies, but here we go. 10, 9, ignition sequence start. 5, 4, 3, 2, 1. I'm seeing.
Okay, and stop. Tranquility Base the Eagle Red Weapon. Rocket tranquility, we copy on the ground. You got a bunch of guys that
Armstrong is on the moon. Neil Armstrong, 38-year-old American, standing on the surface of the moon. On this July 20th, 1969.
That's one small step for man. One giant leap for man.
All right, wow. That's what I missed. Ideally, I'd end my talk now, but I think we've got a little bit of time to kill. So we'll press on here. So just incredible footage of the first of a number of moon landings right there. You can just keep watching that. So Apollo 11, as you've already heard, landed in Mare Tranquillitatis, one of the volcanic plains on the moon. And we have all these just incredible, beautiful, iconic photos that those of you who were here in the last talk saw many of these just incredible photos of people walking on the moon for the first time. I won't belabor the details since you've already heard about this, but Apollo 11, the total mission duration, about 8 days. I like to think of that as a good kind of family vacation kind of period. 8 days trip to the moon. Of that, only less than a day, 21 hours was spent on the lunar surface. 2.5 hours actually spent walking around on the moon, taking pictures. But the Apollo astronauts were not tourists. They did not go there just to walk around and take pictures. They were collecting samples. They were deploying instruments. They were making measurements. They were getting data. They were learning about the moon. And that's really what I want to talk about today. So first, before we go any further, why go to the moon? This is a pressing question. It's a pressing question then, and it's a pressing question now. And again, rather than me try to answer this, I'm going to let history speak for itself. And let's just get that quick clip of the JFK talk.
Why some say the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon in this decade and do the other thing. Not because they are easy, but because they are hard.
Not because they're easy, because they're hard. Just an incredible speech kicking off, this is not the first of his speeches, but an incredible speech kicking off our exploration of the moon. But this was not the last presidential vision for space exploration. So a history of the future, a history of visions of the future of space exploration. Of course, many presidents have had visions for space exploration, but focusing on the ones that had grand ideas about the moon. The first George H.W. Bush, in 1989, his space exploration initiative that he described. In the new century, that would be this century, back to the moon. He envisioned a permanent manned presence on the moon, and then by 2019, this year, a human mission to Mars. Then going to the next Bush, George W. Bush, and his vision for space exploration, he talked about extended human missions to the moon as early as 2015, being sort of our stepping stone to worlds beyond, to people going to Mars. And then now, as you probably know, Mike Pence and Donald Trump have announced their space plan to return Americans to the moon within the next 5 years, by 2024. The first woman and the first men to return to the moon. So these visions for space exploration have evolved over time. The timeline seems to keep getting pushed off further into the future, and yet we are making real progress. We can see progress being made in the launch system and Orion and all of this, so we're looking forward to see what will come of this. But this still leaves this question of why go to the moon? You know, why do all of this? We've heard the estimated price tag from NASA about $20 to $30 billion beyond the existing NASA budget. Is that worth it? Why are we doing these things? So, well, let's start with Kennedy. Not because it is easy, but because it is hard. It's a beautiful speech. It gives me literally goosebumps to listen to that speech. This is sacrilege to say, but really? Because it's hard? I mean, for me, that reminds me, as a kid, looking at the Guinness Book of World Records, of the longest fingernails, the longest hair, holding still for the longest time. Why are people doing these things? They can be the first, and because it's hard, I think we can do better for the moon. So what about, well, to establish American dominance in space, to compete with China and Russia? It used to be the Soviet Union, but we have to add Europe, Japan, India, Israel. And this is something that's talked about a lot. For me personally, as a planetary science, what I find more inspiring is how international space exploration is today, how nations are cooperating to do these things. So this doesn't really quite resonate with me. Extracting resources is something we talk about, and I'm sure that's going to be important in space exploration in the future. National security is something that's talked about, and then this idea that it's just our destiny to go to the moon, which also doesn't quite resonate to me because it just feels too much like Europeans' destiny to colonize the world. None of these, as a lunar scientist, none of these are quite speaking to me. So why go to the moon? Well, for me, when I try to justify this, I go back further than crossing the Atlantic or climbing the highest mountain. I don't ask why rice played Texas. But what I ask is, well, why did the Mayans create the Dresden Codex 3,000 years ago? A book that today can still be used to accurately predict solar eclipses. Why did Bronze Age Europeans, 5,000 years ago, construct stone monuments that align with solar events, celestial events like solstices and standstills? Closer to home, here in this continent, in this part of the country, why did the ancestral Puebloans record the position of the sun, the moon, and a supernova that occurred 1,000 years ago in the night sky? Why did the ancestral Puebloans inscribe rock circles, spirals in the rock that are illuminated by daggers of light only at obscure events, things like the lunar standstill? And if you can find a lunar scientist after this talk, ask them what the lunar standstill is. Yeah. And then 2,000 years ago, why did Eratosthenes travel around the ancient world looking for a well and a post he could use to measure the radius of the Earth? All these things were hard, but that's not why these people did these things. These people did these things out of a drive to understand the world around them. So I would argue that this curiosity, this drive to understand the world, is the essence of our humanity. It's the root of science. It's what makes us human. All animals eat, poop, reproduce, and defend themselves. Those things are great. We need to do those too, but it's our desire to explore. Our inquiry and our exploration is what makes us human. So for me, that's why I think we need to go to the moon. That's why I think we did go to the moon. I've got this quote here from T.S. Eliot that I think is really relevant. "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time." This is a nice quote, but it's also very relevant to the moon. You see, the moon especially, by understanding the moon, I'll try to convince you we will understand Earth, and that's really key. I would argue only by understanding the moon can we truly understand the Earth, like T.S. Eliot is saying here. So now I want to step back in time for me. So as an early graduate student thinking about the moon, in a moment of pure hubris, I made the statement that the moon is boring. I said, we know the moon. All the big questions were answered in Apollo. There's really nothing left to do. I saw the moon as a body with craters on it. It's had volcanism on it, and it's basically a done deal. It's an answered question. I wanted to do water on Mars. That's what I thought was cool. I very, very quickly came to understand that the problem was not that I knew too much about the moon, it was that I knew too little. And the more I learned about the moon, the more I studied the moon, the more I've done research on the moon, the more I've realized how little I understood about the moon then, and how little I understand about the moon now. And that's what excites me about as a lunar scientist, is that I see the moon as one of the most puzzling bodies in the solar system. And scientists love that. There's nothing scientists love more than an unanswered question. And so, what science did we get from Apollo? 6 trips to the moon, walking around on the lunar surface, 6 different locations, talked about some of these, you've seen some pictures of all these, but what did we learn science-wise about the moon, and what remains to be learned that can drive us to go back there again? So the most basic thing you can say about the moon is that there's bright spots and there's dark spots. Go out tonight, you'll see them. You don't believe me, you've all seen them before. The bright regions are called the Highlands. They're these ancient cratered, rugged terrains. The dark areas, these smooth, dark plains, are called the Maria. These are volcanic plains. So as we heard about a little bit in the last talk, this is understanding these 2 types of features was one of the big discoveries of Apollo. And in particularly, these bright highlands here. And these bright highlands on the moon, the samples brought back from Apollo told us about the existence of a magma ocean. The idea that much of the moon was molten in its early history. This is an artist's conception. I'm not sure if this is one of Bill Hartman's paintings or not. I couldn't find a credit for this one, but an artist's conception of what the magma ocean on the moon might have looked like. But we think that much of the lunar surface, at least, was molten. And we think this because the Apollo astronauts, beginning with Apollo 11, brought back samples of the Highlands, that bright, ancient, rugged surface. These are pieces of the lunar highlands here. Even Apollo 11, which landed on the Mare, the volcanic plains, found pieces of the lunar highlands that they brought back. And in fact, this discovery stemmed out of the post-Apollo 11 analyses. That what these highlands are made of is a mineral called plagioclase. Now, I have a hard time getting excited about minerals, but plagioclase, I'm a geophysicist. Apologies to mineralogists. Plagioclase is an important one. Because plagioclase, if the moon was molten, plagioclase is what you'd expect to find at the surface. The reason why is as you've got this molten magma ocean, as it cools and crystallizes, plagioclase floats to the surface because it's less dense, and other minerals sink to the bottom, like olivine and pyroxene, because they're more dense. So from a very simple understanding of how a magma ocean would cool and crystallize, you predict a plagioclase crust on the moon, and then here come these Apollo 11 samples made of plagioclase, proving the existence of a lunar magma ocean. Now, as a graduate student, I thought, okay, case closed, magma ocean, problem solved. Now I see how difficult and tricky this problem actually is. So continued analyses of these lunar samples. People are analyzing Apollo samples even today. An incredible amount of science is still being done with the Apollo samples. And since the Apollo missions, techniques of measuring ages have just continued to improve. So one of the goals is to measure the ages of these rocks. And when we look at this, we find evidence that the moon formed, well, quite a long time ago, potentially 4.53 billion years ago. There's some dispute on every age that I'll put up here as a disclaimer. The oldest known highland rocks are about 4.46 billion years ago. So that's when, at least by that point, we know that the magma ocean had begun crystallizing. And yet across the moon, we find a lot of rocks with ages of about 4.38 billion years ago. Now that's, those numbers sound pretty similar, but we're talking billions of years. This is suggesting that for 150 million years, there was some semblance of a magma ocean remaining on the moon. And that's really interesting and really puzzling. I think one of the key questions in understanding early lunar evolution today is what was the evolution of the magma ocean like? Did it take 150 million years to crystallize? what was going on in the moon at that time. Earliest lunar evolution is a really big puzzle here. Now, magma ocean work has continued to benefit from new data as well as new analyses of old data. So something I'll talk about a little bit later is that we have seismic data from the Apollo missions. This was alluded to in the last talk from the lunar seismometers. Seismic data gives us point measurements of the thickness of the lunar crust. We also have gravity data. Gravity measuring the gravitational field of the moon lets us create models of the thickness of the crust, kind of pinning it to those seismic measurements. So now we've got a pretty good idea of how much plagioclase there is on the moon. Ideally, we could take that and figure out how deep the magma ocean is. The problem is, and this is something that's really only come out in the last several years, is that the devil's in the details. There's a lot of complexities you have to think about to get from magma ocean to crust. Things that we never thought about before. How much water was present in the lunar interior? The answer used to be none, but I'm going to come back to that. It's not none anymore. How efficiently did these crystals separate? It turns out not to be a simple matter to go from magma ocean to crustal thickness. And one of the big questions in lunar science today is, well, how thick was the magma ocean? Was the entire moon molten, like we see here, or did the magma ocean only extend down out to about, say, 500 kilometers or so? There's some fairly interesting observational evidence to support this scenario, and yet most views of the formation of the moon would support this scenario. This is a critical question. If we can answer the question of how deep the lunar magma ocean is, we would know a lot about lunar formation and early lunar evolution. So this is on my list of big unanswered questions in lunar science today. This leads to the question of the origin of the moon. Now, this is something that you'll probably hear about more in the next talk by Bill Hartman. I really encourage you to stick around for that talk, and I'm sure you will, because this idea stems back to Bill's work. So in 1975, he wrote a paper arguing that the moon formed in a giant impact. And that idea has really held sway since that time, that 4.5 billion years ago, an object struck the Earth and launched debris out into space that formed the moon. Now, since that time, a lot of work has been done, kind of refining the details of that picture. There are a lot of really detailed computer models showing what would this giant impact look like. So the prevailing view is a Mars-sized object, referred to as Theia, striking proto-Earth at about a 45-degree angle. And I'll show this animation of what that looks like in a computer model. This incredible impact, launching debris out around the Earth. This cloud of debris flattens into a disk, and then that disk gradually coalesces to form a moon. This model became so well accepted, it explains so many of our observations. It came to be called the canonical moon-forming impact model. It's the canon, it's right, it's like the Bible. You can't disagree with it. This was almost universally accepted. This was on my list of solved problems when I was an early graduate student. Not the problem that I solved, the problem that the community had solved. And yet, a few years go by and it begins to be called into question. So there's a problem, and I'm sure Bill will talk about this more in the next talk, but one observation is that the Earth and Moon have very similar compositions. We have pieces of the Moon brought back by Apollo, we live on the Earth. Every body in the solar system has a unique chemical fingerprint, particularly in the ratios of isotopes in those samples. And one of the early observations was that the Earth and Moon are almost identical. In fact, they seem to be identical before. Now we can measure those subtle, tiny differences between them. But so we had established that the Earth and Moon were almost identical in composition, and yet the canonical moon-forming impact model had the moon forming almost entirely out of the object that struck the Earth, Theia. So these are two different bodies with two different compositions. Why did the Earth and Moon end up with almost identical compositions? It just didn't quite mesh with this canonical moon-forming impact. Now, Bill will talk about this, I presume, in more detail, showing whether that actually is a problem or is not. And there's a lot of debate over the extent to that's a problem. But this opened up the field to a whole new class of impact of moon-forming models, all still variations on that 1975 idea of a giant impact. So in one view, rather than a Mars-sized object striking the Earth, you have two basically half-Earths, a symmetric impact, two objects nearly the same size colliding. Because the object is symmetric, You get a little bit of one and a little bit of the other out in space in roughly equal proportions, and you can make an Earth and Moon that are the same composition, no matter what these two bodies are made out of. And so this is one way to explain the similarity between the Earth and the Moon. Alternatively, it's been proposed that you could do this if the early Earth was spinning incredibly quickly. So if the early Earth was rotating very fast and got struck by a smaller, faster moving projectile, well, the Earth ends up spitting a lot of material out into orbit around it. Because it's rotating so fast, it's shedding material. There's an early idea for the origin of the Moon that had long ago been rejected, the fission hypothesis, that the Earth was rotating so fast to basically spit out a moon. And that was nicely rejected. This is effectively fission version 2.0. The Earth is spinning almost fast enough for fission, and then an impact, triggers all this material going out into space. This can also explain the similar compositions of the Earth and Moon. Alternatively, maybe it wasn't just one giant impact. Maybe it was multiple giant impacts. If you have smaller, faster impacts, they blast more target out into space and have less of your projectile. So a little small object striking the Earth, you end up with more of the Earth out in orbit here. It's not enough to make the Moon, but if you repeat and repeat and repeat, you can put enough material out in orbit around the Earth to make the Moon. And so this multiple impact origin for the Moon is yet another way to make a Moon that's very similar, if not identical in composition to the Earth. Or lastly, what if the Earth and Moon did start out different, but then they became the same? So people have done more and more advanced models of what would the Earth and Moon really have looked like after that giant impact. Those animations I showed you are a little misleading because they only showed stuff that was basically solid or liquid. What you would really get, if this is proto-Earth, it would be surrounded by this disk, this torus, this bizarre structure has been called a synestia. They had to invent a new name for this feature. That's a mixture of vaporized rock, of molten rock, all enveloping the Earth and the disk that forms the Moon. And there's really no clear line between where the Earth ends and this disk begins and where the disk ends and the Moon begins. And this lets you really mix things between the Earth and the Moon in this just incredibly hot, well-mixed vapor melt mixture. The end result, again, no matter what the Earth and Moon were made out of, you end up with the same composition. So this is a way basically of effectively reconciling that canonical model, the Mars-sized impactor, with the data we've got today. Now, the interesting thing here, I'm not going to advocate for any one of these theories, or as I said, it's also possible that the problem may not be as big as previously stated, and you may just be able to do it with a projectile that's made of similar stuff to the Earth. The interesting thing is that we don't actually know the answer here, that there's vigorous debate in the scientific community regarding how the Moon formed, and that's really cool. This is a huge unanswered problem in lunar science. If we go back to T.S. Eliot's quote about understanding the place where we started for the first time, that is where this is really relevant here, because we can't understand the Earth without understanding the formation of the Moon. I would argue that the formation of the Moon is the single biggest thing that happened to the Earth. We wouldn't be here today. The Earth wouldn't be the way it is were it not for the Moon forming impact. We'd just be a completely different planet altogether, and I won't even begin to speculate what that planet would look like. So understanding the Moon and understanding the Earth are really one and the same thing here. On a related topic, all of these impacts hitting the Earth to make the Moon, impacts were hitting the Moon early in its history. And this is another very important discovery that stemmed from Apollo work, and also that Bill Hartman has done some really critical work on. This is an old and a younger surface on the Moon. We've got Highlands, we've got Mars, and we see, okay, there's a lot more craters on the older surface, a lot fewer craters on the younger surface. One of the key things from Apollo was to bring back samples so that we didn't just have to say old and young. We could actually measure ages and put actual dates and ages on these surfaces. Turns out, a very old Highland surface might be only 4.1 billion years old, maybe 4.4. This is pretty hard to pin down, whereas these volcanic Mars surfaces are about 3.5 billion years old. Now, wait a minute, you look at that, and you don't have to be a rocket scientist to put this together. All of these craters formed in the first few hundred million years of the solar system. And then in 3.5 billion years, this is the number of craters that formed. That right there, you can see pretty clearly, there were a lot of impacts early on. and not so many impacts later on. And this is kind of our first order understanding of the history of impacts in the solar system. The vast majority of craters on the moon form in the first 15% of its history. First few hundreds of millions of years, maybe first half a billion years. And then things really quieted down a lot. So one of the key goals of Apollo was to really pin down lunar chronology, to try to find key features on the moon and put ages on them. And one of the most fundamental things to look at were impact basins. We have these giant impact basins all over the moon: Imbrium, Serenitatis, Crisium, Nectaris, and some of the Apollo sites were ideally situated to try to put ages on some of these impact basins. It turns out to actually be a pretty difficult thing to do, and there's uncertainty and vigorous debate over all of these ages. But nevertheless, we have some constraints on the ages of basins, and they're all kind of clustering in this same period of time. So by some estimations, as many as 14 giant impact basins formed in as little as 200 million years. Now, again, there's a lot of argument over the timing of these basins, but this set up the concept of what was going on 4 billion years ago. Did something happen? And so an idea emerged of basically two different views of the bombardment history of the solar system. In one view, at 4 billion years ago, there was something called the late heavy bombardment, a spike of impacts where there were many more impacts than formed before or since, and that this flux of projectiles hitting the moon created all of these basins and many of the craters we see on the surface. Alternatively, and that's kind of shown by here, the spike of impacts at about 3.9 billion years. Alternatively, there's a view that, well, the flux of impacts was really high early on and it was steadily declining, but we're only seeing the latest basins because the later basins are wiping out the early basins. It's a much more nuanced argument that I'm sure you'll hear more about. And then there's other lines of evidence as well. We can look at things like lunar meteorites. This is something that Tim Swindle does, and a number of other people in the field. We can look at other objects like meteorites from the asteroid belt, evidence from Mars, and so on. And this has been a really controversial topic. This fundamental question of how did the rate of impacts evolve in the first 500 million years of solar system history is really critical. These ideas go in and out of favor. For a long time, the late heavy bombardment was the favored model, and it's quickly losing favor now. As a scientist, I tend to kind of take the long view, and I sit back and I'm going to watch the pendulum swing back and forth a few times now, I think, still. But this is really critical because now we're not just talking about moon. We're talking about the bombardment history of the entire solar system. This affects things like the origin of life on Earth, the origin of life on Mars, and the histories of all of the planets, really. So this is also on my list of just fundamental critical questions in lunar science that we're still trying to answer. Now, a really critical pre-Apollo observation came from the Soviet Luna missions. So this is a picture. It's not a good picture, but it is a really, really groundbreaking picture of the far side of the moon from Luna 3. So the Soviets were the first to fly past the moon. Everybody up until that point of time had only been looking at one side of the moon. This is the first time we'd seen the far side of the moon, and boy was it a surprise. We're all used to looking at the near side of the moon, the man on the moon, the bright and the dark, the Maria. The far side of the moon was almost all bright. There were very few Mare. In fact, the one major Maria on the far side of the moon got named Mare Moscoviense, because guess who discovered it? But that's really puzzling. Here, what we've been looking at all of human history, really, was not representative of the entire moon. Why? What's going on there? Let me give a slightly different view. This lunar reconnaissance orbiter image mosaic of the entire moon. This is the far side of the moon, and then the near side of the moon is straddling the edges here. Again, all of the dark Maria, the volcanic plains, are on the near side, with very few Maria on the far side. Well, what if we look at other data sets? Well, let's look at topography. Here, red is high, blue is low, and it looks like the near side is really low in elevation. The far side is really high in elevation. If we use geophysical data to try to get at how thick the crust of the moon is, that plagioclase crust that formed out of the magma ocean, turns out it looks kind of like this. The crust is really thick on the far side, really thin on the near side. Well, that's puzzling too. What if we look at composition? Well, turns out if you look at composition, the near side is really abundant in a mineral called thorium. And the far side, or an element called thorium, the far side is not. We have really high concentrations of thorium on the face of the moon we've been looking at, and very little on the far side. So the moon, very fundamentally, is lopsided. It's asymmetric. If you were to give just one descriptor of the moon, I like to think of it as the meeting somebody on the street. If you're meeting somebody on the street, what is that one thing you want them to know about yourself, or the few things you want them to know about yourself? I say, hi, my name's Jeff. I'm a professor at the University of Arizona. I've got a wife and a 4-year-old daughter, and I really like maple syrup. That's all you need to know about me. What do you need to know about the moon? Well, the moon is lopsided. That is who the moon is. That is what defines the moon. It is a fundamentally lopsided planetary body. Why? Well, let's start with that composition. The composition kind of makes sense. So if we go back to the magma ocean, as the magma ocean was crystallized, plagioclase is floating, the dense minerals are sinking. It's a lot like freezing a bottle of soda. At some point, you're left with the stuff that just doesn't want to freeze. You're left with corn syrup. In the lunar magma ocean, that corn syrup is called KREEP. Potassium, rare earth elements, and phosphorus. This is the stuff that just doesn't want to freeze. It just doesn't want to go into the crystals. It's left in the final dregs of the magma ocean. And that's what we're seeing with the thorium concentration here on the near side. So you have all this thorium in the KREEP train in the near side has come to be called the KREEP train. And if you just take a very simple model, you take, well, let's take what we think the thickness of the lunar crust is. Where does the magma ocean kind of concentrate as it freezes? Well, it concentrates where the crust is thinnest and the topography is the lowest, and that'll put our KREEP there. I think to first order, we know why KREEP is there, crystallization of the magma ocean, and it makes sense why it's in this particular area. What about the problem, though, is that this actually hinges fundamentally on the crust being thicker and thinner in different places, the topography higher and lower, which we still have to explain. Well, why is the topography higher and lower? Why is the far side high and the near side low? A lot of different models to try to explain this, and none of which are entirely convincing. Well, none of which has really come to be proven to be correct or favored. So a really fun idea was actually proposed by a professor here, Eric Askog, at the Lunar and Planetary Lab. I like to call it the giant splat. I don't think Eric would call it this. But if you have a giant impact on the moon, but a very slow giant impact on the moon, it doesn't blast out a crater. It just kind of, well, it does a lot like what a bug on a windshield would do. It just kind of splats onto the moon. And a splat onto the far side can make the far side thicker. There's actually some really interesting arguments as to both how this could work and why this could work. So maybe the far side is thicker because of what's been called a second moon that slowly just kind of hit and stuck to the far side. One explanation. Or maybe we could speed that impact up a little bit because a faster impact will excavate. So maybe the near side is a giant impact crater from a faster collision that instead of splatting on, excavated material out. So the one view, the far side is the impactor. In the other view, the near side is the crater. This could also explain what we're seeing, possibly. And then there's all sorts of other explanations invoking more nerdy things, lots of geophysics, mantle convection, physical processes, things like a floating continent on the near side, effects of earthshine, a possible asymmetric bombardment, asymmetric convection of the magma ocean. My favorite, just from a physics standpoint, is the slosh of the iron core. If the inside of the moon wasn't molten, liquid iron kind of pools up on top of that cool interior and just all sloshes to one side. All of these could make the moon asymmetric, and we don't know the answer. And this is really, really troubling. This asymmetry between the near and far sides of the moon, that defines what the moon is, and we cannot explain it. That's it's impressive to me and pretty frustrating as well. All right, so let's talk about those seismic experiments. So the Apollo astronauts deployed seismometers. We had passive seismometers on Apollos 12, 14, 15, and 16. And these are measuring seismic waves, moonquakes. Turns out we didn't know this. Prior to Apollo, the moon is seismically active. They detected 9 artificial impacts. That's that lunar module kind of crashing back down onto the surface. 1,743 meteorite impacts, 28 shallow moonquakes, at shallow depths near the surface, over 3,000 deep moonquakes. So over 12,000 total seismic events. This is kind of cool. In the last lunar eclipse, or one of the lunar eclipses earlier this year, that flash is a meteorite striking the moon, and it made a flash captured in this picture here. So the moonquakes, with this network of seismometers, you can locate them. You can figure out where the moonquakes were. A number of them were shallow, a number of them were deep. What's curious, this is the near side of the moon. All of the deep moonquakes appear to be on the near side of the moon. What's more curious still is that those deep moonquakes should not be there. If we scale from where we have seismic activity on the Earth, as things get deeper and hotter, you don't get earthquakes deeper in the interior of the Earth. At this depth, you should not have moonquakes on the moon, but they're there. And so here we have more fundamental questions. Why are there no moonquakes on the far side, or are they there but we're just not seeing them? Why are there deep moonquakes? What's going on there? What physics is letting a moonquake happen where on the Earth no earthquakes could happen? And these are questions we still haven't answered. A very recent discovery about seismometers and moonquakes on the moon is that we see some tectonic fault scarps on the moon that look really, really fresh. You know, less than a few tens of millions of years old. And these very fresh scarps line up with at least some of the shallow moonquakes that have been identified from Apollo. So maybe we're actually seeing the faults that ruptured in those moonquakes. That's kind of exciting if that is the case, but this is a very recent discovery using lunar reconnaissance orbiter data. Going deeper into the interior of the moon, another one of those experiments the Apollo astronauts put down was a surface magnetometer. And Lon Hood, again here at LPL, the University of Arizona, did some of the early analyses of the magnetometer data to put a constraint on the structure of the interior. Does the moon have an iron core, and if so, how big? And then subsequent seismic studies were able to do similar analyses. How big is the iron core of the moon? And it turns out the moon does have a core, but it's very small. And this is consistent with ideas of a giant impact. There are a lot of really puzzling observations in here. Possible seismic transitions and changes in depth within the mantle that aren't fully explained. The possibility that the mantle is actually partially molten above the lunar core. And so these are really key observations, but because Apollo only went to the near side of the moon, I can't tell you whether these observations represent the entirety of the moon or only the near side, because remember, the moon is lopsided. There's no reason to think that the interior, the subsurface of the far side, looks like the subsurface of the near side. No, Apollo here was really trailblazing. Now we have a seismometer on Mars. So we've got the InSight lander on Mars, which is now detecting active Mars quakes, and those are going to be analyzed with the knowledge gained from Apollo, comparing that to Apollo data, as well as Earth data. And shortly, I think in a couple of days, Chandrayaan-2 from India is aiming to put a seismometer at the south pole of the moon. That might help answer some of these questions about distribution of moonquakes and so on that we couldn't answer from Apollo. Another experiment that the Apollo astronauts did was a heat flow experiment, trying to measure the heat flow of the moon. They basically took a big probe and hammered it down into the lunar subsurface and used that to measure temperature with depth to get at the heat flow. This goes back to what we talked about before, all the dregs of the magma ocean, that KREEP-rich material, this creepy terrain here. Well, all that stuff is producing a lot of heat, and we're actually seeing that in the Apollo data. Apollo 15, closer to the KREEP terrain, has higher heat flow than Apollo 17. So this is matching up pretty well with some of these ideas of what was going on with the crystallization of the magma ocean. You may have also heard that on Mars, InSight on Mars also has a heat flow probe, but that probe is stuck. It's actually not the first heat flow probe to get stuck, it's about the third. Apollo 15 and 16, they didn't get stuck, but boy, those astronauts had a hard time getting those probes down 2 meters into the subsurface, and there's some interesting transcripts and stories of them trying to get those heat flow probes down in. So another discovery about the moon relates with volcanism. Again, Apollo astronauts bringing back samples of basalt, letting us put actual ages on these volcanic units. And surprisingly, those volcanic units are really, really old, about 3.5 billion years, with volcanism basically tailing off 2 billion years ago. So all those volcanic plains are really old. And this gives the view of the moon today being volcanically dead. Okay, volcanism stopped 1, maybe 2 billion years ago. And yet, recent observations These are lunar reconnaissance orbiter camera pictures, show extremely small but extremely young volcanic deposits within the Maria. These don't look like the rest of the Maria. This is something different, and these are potentially less than 100 million years old, maybe only a few tens of millions of years old. This young volcanism that was only recently discovered is kind of rewriting our volcanic history of the moon, and we still don't have a good understanding of what's going on to produce this young volcanism. Now with volcanism, most volcanism on the moon made of big broad plains, the dark spots, the Maria. We see those all over, but the moon also has volcanoes in the more traditional sense. A volcano building up a mountain. So this is a distribution of a couple of these volcanoes. Here's a picture of some of those. This is actually an Earth-based telescopic image of the Marius Hills. And all these little bumps here are volcanoes. This is actually the backup site for Apollo 15, not the backup. It was an alternate site that was considered for Apollo 15. There's a big push by many people to visit Marius Hills or one of the other volcanoes on the moon. And it's a bit unfortunate that we didn't, because these are really unique. And it's unlike a lot of the other lunar surfaces that we see. This is a topographic map. This is sort of a high elevation area. You can see the little bumps. Those volcanoes are about a few hundred meters high each. And Marius Hills isn't alone. Mons Hanstein or Hanstein Alpha, another one of these volcanic domes, the Groythuizen domes. These are things you can see with a small telescope looking at the moon from your backyard, which is pretty cool, I think. A very recent discovery, these were known back in the Apollo days. Only recently have we gotten constraints on composition. Remote sensing with a satellite around the moon has revealed that these volcanoes are made of a more silica-rich composition than the rest of the basalt, more silicon in the mineral structure. That's not terribly surprising. That's what you expect for these steep-sided volcanoes, but it's unlike all the rest of the volcanism we have on the moon. We have these silica-rich, steep-sided volcanoes in a few isolated locations. What's going on there? And then to make matters even more interesting, if you comb through the Apollo samples, there are just a few tiny, tiny little flecks. There's a couple centimeter piece of a felsite class of a silica-rich material might be representative of those volcanoes. More recently, somebody argued this is actually a piece of Earth, which could also be the case. But again, more questions that are unanswered about the moon. Let's see, I'm going to skip ahead here so we don't run too terribly long. Let's talk about another topic related to volcanism. So one of the Apollo discoveries is that the moon is dry. It is bone dry. You look at the Apollo samples and it was difficult to detect any water at all in them. Estimates on the water content of the moon from the early Apollo analyses had upper limits of about 100,000 times less water than on the Earth. Take all the water in the interior of the moon to the surface, and at most it would be about 1.5 meters. Not a lot. And this was really consistent with the giant impact origin for the moon, that super hot molten start that the early moon had. Now I want to show you, this is a video clip, really more of an audio clip, of a really cool discovery. And I just want to show this because I think this really kind of captures the essence of discovery in Apollo. Let me get to the right spot here. And there. This is Jack Schmidt on Apollo 17. Oh, I started too far.
It's all over. Well, don't. Oh, hey!
There we go.
Wait a minute. What? There's a reflection of it. There is orange soil. Well, don't move it till I see it. It's all over. Orange. Don't move it till I see it.
So that to me is what Apollo is about. For all the Apollo videos, the video is horrible, but that's the essence of Apollo. Walking around the moon and seeing something and discovering something. That orange soil turned out to be hugely important. That orange soil was glass beads from a fire fountain eruption. This is on the Earth. That did not happen during Apollo 17. These fire fountain eruptions, this magma shooting up out of the moon, propelled by some sort of gas, maybe carbon monoxide, maybe water. At the time, it became universally accepted, widely accepted, that carbon monoxide was what was going on there because it was known that there was no water on the moon. Only recently has this story changed. It turns out if you look really closely at those glass beads, they do have water in them. And if you look at other samples with the precise enough equipment, you can measure water in other lunar samples as well. One of our newest faculty, Jessica Barnes, is one of the experts now in lunar water. This is a field that didn't exist before. But it turns out pockets within the moon have as much water as the Earth's mantle. And that's crazy. And that's a little difficult to reconcile with this idea of a magma ocean. So understanding why there's water on the moon is a critical question in terms of understanding the magma ocean. Now, lastly, I'll just talk a little bit about tectonics on the moon. So we talked about moonquakes and about seismicity, how the moon has some tectonic activity. Deep moonquakes, don't know what's happening there. Shallow moonquakes, well, that's probably more like an earthquake on the Earth. And we do see tectonics on the moon. So we see these tectonic structures, wrinkles where the crust is wrinkling up and folding, these graben, these troughs where the crust is extending. And these have been nicely explained in terms of what we think we understand about lunar evolution. You pile a bunch of lava on one part of the planet, and the surface deforms, and it cracks, and it bunches up, and you get faulting. The moon is cooling off slowly over time, and while it cools, it contracts, and you get some folding, and you get some faulting. And this was a very comfortable view of the tectonic evolution of the moon, and that's all there is to it. And then we started looking in gravity data. This is data from NASA's Rille mission, getting incredibly high resolution gravity data from the moon. On the near side of the moon, in gravity data, we see just this crazy polygonal structure. This is kind of a projection of the same thing. It's a giant square on the near side of the moon that you don't see at the surface. You don't see in any other data set, but it completely dominates the gravity field. Trying to understand what these gravity anomalies are in this feature that only exists beneath the surface of the moon, well, when we take the gravity data and we model it, it fits well if the crust was thinning. If along these lines here, if the crust was extending and thinning and stretching out, then that, and then gets flooded with the lava that we see at the surface, that would give us the gravity anomalies we see. Well, how can you do something like that? On the Earth, you do that by rifting. Things like the East African rift zone here and the triple junction in Afar. If you took something like this, that might explain what we see on the moon. And in fact, when I take East Africa, and I can do this because I'm a geophysicist, when I flood East Africa with lava, the gravity field looks just like the gravity field we're seeing on the moon. But that does not fit with our tectonic understanding of the moon. There's no way that we can reconcile this with our conventional view of lunar tectonics. This tells us early in lunar history, it was incredibly tectonically active. And we still don't understand how or why that was happening, that these ancient rift zones formed and then were flooded with lava. So this big question then remains of what was early tectonic activity like on the moon and what was driving that tectonic evolution? So I think that's a good place to wrap up here and just say, you know, going back to what I thought as a naive young grad student where the moon is an answered question, that's clearly not the case. So why should we go back to the moon? I think we should go back to the moon to answer the big questions. There's so much we don't understand about the moon, and along with that, so much we don't understand about the Earth and the solar system as a whole. All of these questions are just fundamental to lunar science, to planetary science, and to Earth science. And for me, that's kind of my motivation for studying the moon and why I think we should go back to the moon. And I'll end there.
You were talking about the lopsided elevation. What's your reference for measuring?
Yes. So the moon does not have a sea level, is a problem. And so what we do with the moon with most planetary bodies, we take an equipotential surface, which is basically what the sea level would be if you had a fluid there to define it. So in studying the gravity field, we can define an equipotential surface, or another way to do it is we just reference it to the center of mass. Sort of two different ways of referencing elevation. Good question.
Other questions?
What equipment is up there now, like today? What equipment is up there actively sending, seismic data, whatever?
Actively.
Yeah.
Well, shortly, fingers crossed, Chandrayaan-2 was supposed to launch a week ago. I think it's the 22nd, they're saying, which is actually supposed to put a seismometer at the south pole of the moon. I believe it's only supposed to be active for one lunar day, but you never know. That would be amazing to get new seismic data because we've not had seismic data since Apollo. And then as was mentioned previously, these lunar retroreflectors. It's just a corner cube here. And they're still active because Congress can't turn it off. They would have had to send Apollo 18 to the moon to retrieve the corner retroreflector. And even the government isn't that foolish.
Yeah, right there. Yeah.
How do you define soil on the moon?
Soil, many people take issue with the word soil. So strictly speaking, we should say regolith as the pulverized upper material. And then soil, Mars arguably has a soil being something that involves more weathering and aqueous processes. That gets into semantics. But strictly speaking, we should call it regolith, that loose upper material, which then even that becomes a little bit of a slippery slope, because then where does that transition occur? Because it turns out you don't just have regolith sitting on top of bedrock. It's much more of a gray transition, and it turns out that the moon is pulverized to much greater depths than we thought before, probably tens of kilometers.
Okay, other questions up there and then there.
Could you tell us a little bit about the Rille's? Be there mystery.
There's a couple of slides I skipped because I was running long, but so the Rilles, here's Apollo 15 at Hadley Rille. Let's start my talk all over again. One cool recent discovery, so these were thought to be, for the most part, lava drainage. Well, for the most part, two things, either lava drainage channels or collapsed lunar lava tubes. And then a recent discovery, the picture on the right is the moon, the picture on the left is not. No sun hat and fanny pack, not Apollo. From the Lunar Reconnaissance Orbiter, as well as the KREEP spacecraft, you see these pits, the collapsed roofs of lava tubes. There are open lava tubes beneath the surface of the moon that, minus sun hat and fanny pack, we could go and explore. It'd be a great place for bases. So there's a lot of interest in those lava tubes.
And let's see, there on in
The
there.
Chinese have a lander on the backside of the moon right now. Have
Yes.
you heard anything about composition, or have they released any data?
I haven't been following their compositional results or remote sensing, because so they had a lander as well that was going to do, they've got some nice images that I haven't seen any of the compositional results, so I'm not quite sure what science is coming of that yet, but very good question.
And there will be.
Yes.
Yeah.
So in the absence of the Apollo missions or other missions that are going to the moon, where is the field getting the data that it's using for these debates that you described?
Well, we do a lot with orbital data. Orbital data has really, especially in the last decade or so, data like spectroscopy for surface composition, topography, gravity, some more recent radar measurements that were also done during Apollo. That has really been game-changing in lunar science in recent years. And now, with the Chinese mission, with Chandrayaan-2, and with the US plans, with the attempted Israeli lander, we're getting back into surface science again. But all of those orbital data sets have also been really instrumental in lunar science.
And I'll put on my sample analyst hat and point out that the other thing that's happened is that we have Apollo samples, which doesn't seem like something new, but new technique get invented. And Jeff mentioned Jessica Barnes, who uses a technique that wasn't invented at the time Apollo was around, but is doing cutting edge lunar research now with those same samples, because she can do things that nobody could do then.
What can she do now?
Find water in individual grains. Has the precision to do that. Other question here and then there.
Other planets in our solar system have moons. Can we extrapolate the data that we use for our moon into their moons?
Very good question. I'm just going to throw this up because I put this graphic together and didn't have a use for it. This is actually how all the moons in the solar system look from the surfaces of their planets. I just think our moon is pretty cool in that perspective, but Pluto wins with Charon over there. That is one key thing from Apollo, though, is what from Apollo can we extrapolate to other planets, as well as from other missions. So, like, our gravity field for the moon is better than any other planets. And we realized a lot of the assumptions we made for the moon were wrong once we got the data to test them. Now we go back and look at those other planets and think, I'm not feeling so good about that assumption anymore. Things like the density of the crust, how porous the crust was, things like, with the seismometers. the seismic data we have from the moon is going to be instrumental in interpreting the seismic data we have from Mars. So I think a lot of things do transfer over, and yet at the same time, the moon is unique in the solar system. There's really nothing like the moon. So you do have to be a little careful in sort of translating science from one body to another.
So none of the, no microbes that we took from here could have gone there, stayed there, and still lived. I mean,
Never say never. Just wash your hands. Sterilizing is hard to do, and that's was the lesson from bringing back a piece of Surveyor.
and then, so in the water, I mean, that's not a place for life.
For like the water, the ice at the poles, which I didn't talk about at all.
For Moon's own life.
Yeah, it would be very difficult. Never say never, but it's among the last places I would look in the solar system.
And the last question, just for a base on Mars, what in your memory would that look like? Like in terms of like where we get like all our, what do they wear? I mean, like, is it going to be self-sustaining in a biosphere, or where that lava well? Like,
yeah, I don't know. I don't know. I think truth can be stranger than fiction sometimes. Lava tubes, there's a lot of interest in because they can protect you from things like meteorite impacts and radiation and so on. But I think we will have to wait and see. Hopefully, we will see.
Okay. I think we are out of time, so let's thank Jeff.